Coming back to the process we want to describe, we have almost all the ingredients, but we still have some work to do for the interaction. We know that such process is described in quantum field theory by a path integral. However, we only worked out path integrals usually only for one field, like the scalar field here, but in order to describe such a process, we will need three fields: the electron field, muon field, and the photon field. And because the electron field and muon field are non-Hermitian, we will also need the psi bar component as well. So we know how to propagate disturbance of these fields in free field theory, so without interaction. We did that with the Klein-Gordon Lagrangian for spin zero real scalar fields, and we also saw the case of complex fields, and we got the Klein-Gordon propagator. We did that with spin 1, in which case we had the Maxwell Lagrangian when the mass is 0, or with an additional mass term if needed, and we got the corresponding propagator, which now has Lorentz indices. And we also did it for fermions, for spin 1 half fermions, and that's given by the Dirac Lagrangian. And we also got the corresponding propagator in momentum space, which involves gamma matrices. We saw some simple cases of interactions for scalar fields. We saw the Fifo theory, where there is only one real scalar field. And the Fifo theory can be seen as an effective theory involving two scalar fields, with one of the fields playing the role of a mediator of the interaction. And in the case of the Fifo theory, we saw how to describe processes like collision or decay, or even particle creation, using perturbation theory, so when lambda is small. And to do that in a convenient way, we introduce Feinman diagrams, so we have to write all the diagrams for a given process, and we truncate to the relevant order. So the first diagram is the first order, so it's only first order in lambda. The other three diagrams are second order in lambda. For obvious topology reason, we call this a tree diagram, while these one are called loop diagrams. But the loop diagrams turn out to diverge when we integrate over momenta for the internal lines from -infinity to +infinity. And that's obviously a problem, because in perturbation theory we expect the second order to be smaller than the first order and not to be infinite. In fact, we should keep in mind that this is only an effective theory, which is only valid at low energy, or at least energies which are smaller than the mass scale for the mediator. So that introduces a cutoff in the integrals, which then regularize these loop diagrams. However, for fundamental theory, where we don't have such natural cutoff, we need to go beyond this regularization process, and we need to introduce renormalization. We are not going to see renormalization. That's going beyond the scope of this course. However, we see that this process at the lowest order is described by a tree diagram with two vertices, so we should be able to calculate its associated amplitude. However, we still have some work to do for the interaction part of the Lagrangian, because so far we only looked at interaction terms which involve only scalar fields, while we see that here we have fermions in interaction. And in this case, the interaction occurs through the exchange of a vector boson, and that will be described by quantum electrodynamics, or QED. Before we get there, we will look at a simpler theory where the exchange mediating the interaction between fermions is done via a scalar field with spin 0. And that's called the Yukawa theory.